Balancing chemical equations. In an equation in math, both sides must be equal. That's the same way it is here in chemistry and physics, and according to what our class is called. But anyway, we have this, which is like an equation, except instead of equal sign, you have an arrow. Now, in balancing a chemical equation, you have to, there are some numbers that you can't change. The numbers that you cannot change are these subscripts. But the numbers you can change are the coefficients. Now remember, these are called coefficients. And I'm not going to write it all out. I think it's going to be, oh, in fact, here it is right here. The coefficients are in front of the number, in front of the compounds, and the subscripts have the ratio of atoms to all the others in there. And that's why you cannot change these, because if you were to say make this a 3, it changes what this is, some kind of silver sulfate or something like that. But it changes what it is. So that's why you cannot mess with these subscripts. And I actually saw a video not long ago where they recommended, before you start making changes to the coefficients, to put all these compounds and elements inside a box. And what that did is that prevented you from changing these subscripts, because you can't change the subscripts. The only things you can change are the coefficients. So that's something that I don't necessarily do, but it's something that might help you if you see that you're having trouble with not changing these little subscripts here. Now, one thing of note is that the arrows are pronounced as yields. So this compound plus this compound yields this compound plus that compound. And the reason it has to be equal, we mentioned it has to be equal, is because the law of conservation of mass. We actually said that before, where if you have, say, a fire, you have lots of boxes out here outside and you set fire to them. The cardboard is going to burn up, and it looks like there's a whole lot less left in the ash, but you have a chemical reaction where gas is let go, and the smoke carries that gas away. And just like we've said before, you have to have an equal amount starting as you had finishing. So it's the law of conservation of mass that makes these equations have to be equal. Well, why don't we go ahead and start looking at some chemical equations. Here you have an unbalanced equation. All you have is just the elements and the compounds. So this is where, if you were to put boxes around them, you'd go ahead and put boxes around them. But you have to have the same number of everything on each side. Let's say on zinc we have one here and we have one here. So that looks pretty good. Zinc has one. The H's. Okay, the H's, we have one here. Oh, we have two H's here. So that's one we're going to have to end up changing. So the Cl's, what do we have as far as Cl? We have one Cl here and two Cl here. So we're going to have to make some changes here. So we have one H on one side and two on the other, and same thing with Cl. So we're going to have to make these numbers match. And remember, all we can change are the coefficients. We can't go changing this 2 or this 2 here. So, what can we do to make these match up? Let's start first of all with the H's. If there are two H's over here, what we could do is make two H's over here and put a 2 in front. So let's see what that does. So that means we have two H's over here and the two H's over there. What about Cl's? Yes, we have two Cl's over here, and yes, we have two Cl's over there. So that makes 2. Now, whenever I'm doing these, I don't necessarily make a element inventory like I did down here. But if I had some that were very complicated, I probably would. So just like putting boxes around these so you don't use the subscripts, this is another tool you can use, making an element inventory to make it to where you can figure these out a little bit. Why don't we take a look at this one? We have two H's here and two H's here. That seems to work out. We have two O's here, but we do not have two O's here. So how can we get two O's over here? I guess we'll have to put a 2 in front. So we have two O's and two O's, but you see what that did to the H's? We now have four H's. And we only had two H's over here. So what do we do in front here to make it four H's? We do that. 2 times 2 is 4, and 2 times 2 is 4. So that leaves 4 H's and the 2 oxygens. Do you get how to do this now? Why don't we have some more practice? You know, in class we're going to have a bunch of practice. This one's a little bit more challenging. Looks like we have 3 C's on this side and only 1 C here. Looks like we have 8 H's here and only 2 H's here. Looks like we have 2 O's here and 1, 2, 3 O's here. Wow, we're going to have to change every last one of them. Why don't you do this? Why don't you right now try to figure out what the answer is while I do this as well. 3 here, 3 here. I'll put this here. So that leaves 3 C's and 3 C's. I'm kind of talking to myself while you're figuring this out as well. Okay, so H's, if I have 8 H's here, I'll put 4 here. So 4 times 2 is 8, so that matches up the C's, and that matches up the H's. So let's see if we can match up the O's. We have 2 O's here. 3 times 2 is 6 plus 4. So we have 4 O's here, 6 O's here, so that's 10 O's on this side. Hey, I'll just put a 5 right here. So I think that's got it. We have 3 C's, we have 8 H's, and we have 10 O's. Did you get it that way? I hope so. Well, anyway, let's go to the next one. And the reason I have this next one here is because of this polyatomic ion. This polyatomic ion here is just going to be easier to treat this NO3, as one element. And in most cases, it acts just like one element. So whenever you're figuring out what goes where, treat it as one. So we'll go about, we have 1 Cu and 1 Cu. That's good. 1 Ag and 1 Ag. That's good. 1 NO3 and 2 NO3. See, that's so much better than looking at the N's and looking at the O's and doing them separately and then trying to figure it out. So how can we get 2 NO3s over here? We can do that, and that adjusts the number of Ags. So we can do that. Ag, I believe, is silver, so I think that would equal it all out. Very good right there. But I have this example here to show you that there will be some instances where a polyatomic ion like NO3 is going to be split up. And if you see that it's split up, you have to do it the old-fashioned way. You have to figure out the number of K's, figure out the number of N's, and figure out the number of O's. And looking here, it looks like the K's and the N's are fine. It's such as you have 3 O's here, and you have 4 O's here. So I think if I put a 2 here, that would mean 2 times 6. And if I put a 2 here, that just might do it. So I have 2 K's, 2 N's, 6 O's, And 4 plus 2 is 6 O's right there. So I think that will work out well right there. Okay, I need to tell you about these 7 elements. N, O, F, C, L, B, R, I, and H. They just are not found in nature by themselves. You just don't find little O's floating around in the atmosphere. I know that's oxygen, but you always find them in the form of O2 or O3 as ozone. But you just do not find these 7 elements alone. They are called diatomic, and you can see diatomic down here is how that is spelled. These diatomic elements, whenever you have a equation like this, it's not going to be like this. You just do not find H's by themselves. You do not find O's by themselves. So you will not have a formula that looks like this. Now, I'm not messing with the subscripts. I'm just putting what is true in nature, because you will only find it to where H's have at least 2 and where O's have at least 2. So that's where you would start your process in this case. So you would have to figure out the balance here. You have the 2 H's, you have the 2 H's, but you'll have to add an O here. So that means you'd have to add a 2 here. And I believe that would balance out 4 H's, 2 O's everywhere. So just know that these diatomic elements are like that. Now these diatomic molecules, is what I should have called them, are easy to figure out. If you look on this periodic table, you have these 7 right here. 1, 2, 3, 4, 5, 6. 6 of these 7 make a letter 7. Isn't that something? And nitrogen starts with the atomic number of 7. I think it says all that right here. And don't forget to put hydrogen in there also. So these are the 7 elements that are diatomic and will only have a 2 beside it, and they will not normally be found without that in there. Oh, let's see what else we have. Hey, what if we have some word problems? I know you have word problems in math where you have to write out equations. Sometimes you do in science as well. So we'll have to take what we know about what these are called. Carbon disulfide reacts with oxygen to produce carbon dioxide and sulfur dioxide. So you may remember carbon disulfide, sulfide, has a 2 here because this is an ionic compound. So you take carbon disulfide and it reacts with oxygen. Hey, you can't just put regular O. It's a diatomic molecule, so you have to put O2. And it yields or produces, looks like carbon dioxide, since these are covalent compounds. I think I said the wrong thing over here. Covalent are the ones that have these dyes in front of them. It would be CO2 plus sulfur dioxide. Oh, we're getting a lot of di prefixes in there, so it'll look like that. But are we finished? No, we have to make sure everything balances out. Let's see, we have the right number of C's. We only have 1 S over there, so, oh, yeah, that O is right there, so we'll have to put a 2 right here. How many O's do we have there? Oh, we got too many O's over here, so that's 6 O's, so we'll have to balance it out like that. I believe that is correct. Hey, I'm running out of time. I better tell you what a mole is. Don't let the word mole confuse you. It is like a unit. The mole ratio equals the coefficient in a balanced equation. Now, here's what happens. In real life, you don't just have 1 molecule of this and 3 molecules of this and 1 of this and 2 of this. You have bunches of them. But these coefficients would be called the mole units. So in a balanced equation, you'll have the ratio of 1 of these to 3 of these equals 1 of these to 2 of these. And that's what a mole ratio is. Hey, I hope you've learned a little bit about balancing chemical equations.